Neuromuscular system adaptations. The first neuromuscular adaptation to exercise is fast glycolytic and fast oxidative glycolytic muscle fibers changing. As a result of anaerobic exercise, these muscle fibers may increase in size. This is known as hypertrophy. Muscle fibers get damaged during anaerobic exercise, such as weightlifting, like a squat. This will damage muscle fibers in the quadricep and glutes, causing mini micro tears. These micro tears have to be repaired by an active recovery over a period of time. When the muscle fiber is repaired, it becomes slightly bigger, which is the increased cross-sectional area of the muscle, as there is an increased number of myofibrils and connective tissue. Therefore, over a long period of time of resistance anaerobic training, this will lead to more muscle tears each session, and then will increase the size of the muscle, meaning that more power will be able to be produced. This is essential for a shot put player, as each time they train, they will create tears in the muscle fiber, and after a long period of time of training, they will get an increase in cross-sectional size of the muscle fiber, meaning that they will then be able to throw the shot put further as the size of their muscles are bigger. It is also important for games players, as the adaptation of FOG and fast glycolytic fibers will mean that they are able to produce more power when sprinting for the ball in hockey, for example, which will be beneficial as they can reach the ball faster. Hyperplasia is similar to hypertrophy. However, hypertrophy is the increase in size of the number of myofibrils, increasing the cross-sectional size of the muscle, whereas hyperplasia is the splitting of muscle cells adding to muscle growth. It has the same benefits of hypertrophy, which is to increase muscle size, leading to more power, which will aid hockey players, for example, and shot put performers in the same way. Hypertrophy and hyperplasia can differ from females compared to men. Usually, men gain more muscle from hypertrophy and hyperplasia than females due to hormones. Men produce more testosterone, which is a male hormone essential for building muscle. Women tend to have less testosterone, which is a reason why men tend to gain more muscle as a result of the same anaerobic training. This does not mean, however, that women can't build muscle. It usually just means that they will build less of the muscle than men. Another adaptation to anaerobic exercise is tendon strength and force generation. Connective tendons become stronger as a result of anaerobic training for a long period of time. This adaptation occurs because they meet the demands of exercise and they have to adapt to this exercise, otherwise an injury will occur. This is good for athletes who play hockey because there is a lot of stress on the connective tissues from turning constantly and landing heavily, especially on the ankles. Thus, strength training and anaerobic training is beneficial for reducing injury. Force generation will also be adapted during anaerobic exercise after a long period of time because the muscle size of the fast oxidative glycolytic and fast glycolytic fibers will be increased. The amount of force that muscle is able to produce depends on its size, so the larger the muscle, the more force it can produce. Strength and force mean the same thing in this context. So as the FOG and fast glycolytic muscle fibers increase in size, so will the force generated in the performer. For example, a shot put athlete who trains anaerobically for the upper part of their body, their muscle size will increase in size so they can throw it further. The muscle tone is also changed as a result of long-term anaerobic training. Muscle tone refers to how much the muscle is contracted at rest, and the more muscle tone means the muscles will be firmer at rest. Muscle tone helps performers with posture. Those who have bad posture are more at risk of injury, and therefore is a benefit for performers who have better muscle tone. Another neuromuscular adaptation that occurs is motor units. A motor unit is the motor neuron and the muscle fibers it intervenes with. From a long period of anaerobic exercise, the adaptation will be that more motor units are summated faster, meaning that a lot of impulses will be sent to the target muscles all at once. This is beneficial to athletes as it means that they will be able to contract muscles faster. Also, another adaptation is neural pathway efficiency. After a long period of time anaerobically training, there will be cellular adaptations and modifications of the neurotransmitters. The neural pathways linking to motor units become more efficient at transmitting the stimulus, which will then lead to target muscles being able to contract more quickly in response to the stimulation. This is beneficial for hockey players, for example, as when they need to sprint to the ball, the performer will be able to contract muscles in the leg faster, meaning that they can get up to speed quicker. This is helpful as it may mean that they can reach the ball before a different player. Motor unit recruitment will also be adapted too. Resistance training helps to increase the additional units of motor units in response to a neural stimulation. This can lead to an increase in force generated, as there will be more muscle fibers activated to create more force when contracting. As the neural pathways become more efficient, this will result in an increased reaction time, because it means that we can communicate more efficiently from our senses to then our brain and the motor neuron to the muscles to produce a movement and thus a reaction. This is very important and beneficial for all games players, in particular goalkeepers, like in football, because the faster the neural pathway efficiency will result in a quicker reaction time, meaning that they will be able to save shots that come at them faster and potentially prevent goals. Having a fast reaction time is a very important aspect in saving shots. Nervous inhibition. When anaerobically training, nervous inhibition is decreased. This means that muscles are able to produce more force and put themselves under more pressure. Nervous inhibition is the prevention of muscles overworking, acting like a safety method to prevent injury. However, anaerobically training will help to reduce nervous inhibition, which will mean in the long term an increase in muscle size from hypertrophy, as it means more weight can be used to put the body under more stress. The proprioceptors will also adapt as a result of anaerobic training. This is because strength training and resistance training requires balance, coordination, agility, and power. The anaerobic training will challenge the normal range of motion of the client, and this causes the proprioceptors to adapt. Balance is adapted by training, as it's the body's ability to correct itself, and the proprioceptive feedback is improved. Also, as a result of muscles improving in strength, such as the abdominal muscles, this will lead to a more stable core and better proprioceptive feedback once again. The speed at which a performer can pull off a recovery is improved as well, as the ability to be more reactive. So, the proprioceptive feedback is improved, meaning that a performer can mentally be quicker to react to a situation. Proprioceptive adaptation is beneficial for performers, as it means that they are going to be able to react to situations faster, and their balance is going to be better. For example, a 100-meter sprinter is going to benefit from the adaptation, as when the gun goes off at the start of the race, they will be able to react quicker, and the balance from the increase in strength and stability of the core, for example, will prevent them from losing balance. So it means that they're going to be able to get up to speed faster, and they have a better chance of winning. On the right hand side of the slide you can see a Wingate test. As a result of neuromuscular adaptations, there are many differences in the graph. One difference that could be made after neuromuscular adaptations is the increase in peak power. This is due to increase in cross-sectional size of the fast oxidative glycolytic and fast glycolytic muscle fibers. And as we know, and as we've talked about, bigger muscles can produce more force. This is why the peak power increases from 15 to around 19. Another adaptation that is shown in the graph is the line labelled reached peak power faster. This is because, as a result of more efficient neural pathways, there is an increased reaction time, which means that as soon as the test starts, the muscles will be able to contract quicker, meaning that the peak power will be able to be reached faster. The graphs show this as before adaptations it takes around 3 seconds, whereas after adaptations it will take around 2 seconds. There are also energy system adaptations as a result of anaerobic training. Anaerobic training can also cause significant changes. Firstly, for the ATP-PC system, anaerobic training consistently can lead to increased levels of ATP and PC in the muscle and an increased capacity to generate ATP in the ATP-PC system. A reason for this is due to the increased activity of enzymes such as creatine kinase. This will mean that the PC is broken down faster, meaning that the energy creating from the splitting of phosphocreatine can be used to stick the P back on ADP to create ATP energy. As a result of this, it means that energy will be available faster, so that the muscle can contract quicker, and thus a better speed in sporting examples such as hockey, where a player may have to sprint onto a through ball, therefore it is beneficial for games players. Another adaptation to energy systems is the anaerobic glycolytic system, as the ATP production is increased from long-term adaptations to anaerobic exercise. The reason why ATP production is increased is due to enhanced use and activity of the glycolytic enzymes, and the enhanced ability to be able to break down glucose with no oxygen. There is also an increased ability by the body to store a greater amount of phosphocreatine, which will enable short bursts of high-intensity exercise. The onset of blood lactate accumulation, or OBLA, will also be adapted from anaerobic training. If a performer consistently trains anaerobically for a long period of time, the body will adapt to the increased level of lactic acid, and pain of building up lactic acid will be reduced. The pain of the lactic acid. This means that performers are able to work for longer, as they do not feel like they are forced to stop from the build-up of the lactic acid. Therefore, the OBLA will be reduced. As you can see in the graph on the left, this is before anaerobic training. The lactate threshold is around 11.8 km per hour. That's where the lactic threshold starts. However, if a person trains anaerobically, they will have a prolonged lactate threshold, and it will start at the speed of around 13 to 14 km per hour. This is extremely beneficial for athletes running the 400-meter sprint, for example, as it means they are able to work at higher intensities for longer, and the energy system will not change as quickly, meaning that more power and speed can occur before the lactic acid starts to build up. After the lactic acid builds up, they will slow the performer down, as the glycolytic enzymes are inhibited, meaning the energy system will change to aerobic. The performer will slow down, as the aerobic system allows for lower intensity, higher duration, and not high intensity. This is not beneficial for 400-meter sprinters, as they want the fastest time possible. Therefore, performers who can have a delayed onset blood accumulation will gain a better time, as they can work for a longer anaerobically. The body also becomes more efficient at buffering the lactic acid and becoming tolerant towards it, which helps to reduce the onset of blood lactate accumulation. This is because long-term training of the anaerobic system results in the body increasing the buffering capacity of the body and enables the body to work at higher intensities for longer. This will also help to reduce the ABLA, as talked about earlier. This is beneficial for athletes as it means that they can work for longer, as they are more tolerant towards the build-up of the lactic acid. For example, for game players such as in football, when a player has a part of the match whereby they have to use the anaerobic system for a longer period of time, meaning they are working at higher intensity for longer, the more they are tolerant to the lactic acid that will be built up, means that they will be able to work harder for longer. So for example, if they're sprinting towards the ball, they won't get as tired and may get there before a defender if they've already done so a couple times before this, because the lactic acid, they've become more tolerant towards it. As you can see in the figure on the right, showing the changes in blood lactate during a Wingate test, before adaptations, this is what the graph looks like with the resting blood lactate level at around 1.5 millimoles, and post-test the lactate levels is around 7.5 millimoles. However, after adaptations, the blood lactate levels would show lower pre-test at around 1 millimole. The reason for this is because the body has become more efficient at reducing the level of blood lactate in the body, as there is more efficient circulation, and thus diffusion occurs much faster, and then CO2 is expelled from the body. Then post-test, the reading for blood lactate would also decrease to around 6.5 millimoles. This is because the body has built up a resilience to the lactate build-up and have buffered the increase in lactate, meaning that the performer will be able to work for longer at higher power output during the Wingate test. In slide 1, the Wingate test adaptations were shown. As another adaptation of lactate buffering and tolerance, this would be the line that would be shown to sustain higher power for longer. The basal metabolic rate will also be affected as a result of long-term anaerobic training. The basal metabolic rate will increase as a result of the training, because the International Journal of Exercise found that resistance training anaerobically has been shown to elicit fat-free mass-related increase in basal metabolic rate. As the volume of resistance training increases, so did the metabolic rate. That's what they found. The basal metabolic rate is the number of calories that the body is burning at rest to keep the body functioning. Genetics does play a big role in the BMR, as some people will have a naturally high metabolism, and some will have a much lower metabolism, meaning that they don't need to burn as many calories, and thus may carry more body fat, as carbohydrates may turn into the body fat if they aren't burned because they have a lower BMR. The reason why anaerobic training increases the basal metabolic rate is because the body becomes more efficient at using calories, for example. It's like a car. Having a better engine inside of a car is going to use more calories but have more power, and having a high BMR is beneficial to some athletes, such as a boxer, because it means that we will carry less unnecessary body fat, and they may be faster in their punches and jabs, for example, catching opponents off guard.